Welcome back. Hopefully you've already taken your quiz over confidence intervals for a single population proportion. If not, make sure you do that now. There's also a homework assignment that you should probably do, work on that as well before you watch this one. Because we're going to table discussion of confidence intervals for a little bit. We're going to switch gears. And to do that, we're going to work on a brand new example here. So, suppose it has been estimated that at any given time, 90% of adult Hoosiers can identify the current POTUS. That's President of the United States. So we're assuming 90% of adults in Indiana can identify who the president is at any given time. This is totally made up. I have no idea what the true proportion is. That seems reasonable to me, but in reality it could be a lot different than that. But we will assume that that is the case. You want to estimate this proportion to determine if it's reasonable, which seems like an interesting thing that you could do. So you take a random sample of 400 Hoosiers and ask each who the president is. 376 of them correctly answer Donald Trump. And I believe at the time I upload this video, he is the president. By the time that you're watching it, I believe Inauguration Day will still be about a week away, so he will still be president. But then obviously it will be Joe Biden. And if you're listening to this in the distant future, it's an interesting time in late 2020, early 2021. All right, so that's the information we have. And what we want to figure out is, does this sample provide strong enough evidence to suggest that the true proportion is higher than 90%? Okay. So we're assuming that the true population proportion is 90%. We took a sample, we've got some results, and we want to know whether that sample provides evidence that maybe that proportion of 90% is inaccurate. Is it actually higher than that? Because if you take 376 out of 400, you'll find that that is greater than 90%. But do we have strong enough evidence from this relatively small sample to suggest that that's enough, that that's strong enough evidence that P is actually bigger than 0.9? How could we figure that out? How can we answer this? How do we know if there's strong enough evidence? Well, we could use what we just learned in the last few videos. We could calculate a confidence interval for P, the true population proportion of adult Hoosiers that can correctly identify the president. But we usually only want to use confidence intervals if we're asked to do so. And that's because confidence intervals work in a very specific way, and we want to know if there's strong enough evidence to suggest that P is greater than 0.9. To answer questions such as this, we're not going to use a confidence interval. We're going to use what's called a hypothesis test. So in order to answer questions such as this one, is there enough evidence to prove something? We want to conduct what's called a hypothesis test. And it turns out there are multiple parallels between a hypothesis test and what we in America do in a trial by jury. That might seem a little strange to compare those two things, but here we go. In a trial by jury, the jury has to determine whether the defendant, whoever is being accused of something, is guilty or not. And in a hypothesis test, we need to determine whether a parameter is greater than, less than, or not equal to a certain value. So in a trial by jury, we're interested in whether the defendant is guilty or not. And in a hypothesis test, where we are interested in whether a parameter is greater than, less than, or not equal to a certain value or not. In this particular case, for this hypothesis test, we want to know if the parameter is higher than 90%, so greater than. We could ask a question about whether the true proportion is less than a certain value or not equal to a certain value as well. And we'll get into those in further examples. So that's one of the things we are looking at here. And we will be able to determine whether the parameter is any of those things based on the same sampling distribution of p hat that we used to calculate probabilities in Unit 5, and the same model that we used earlier in Unit 6, just a few videos ago, to calculate confidence intervals. It's the same idea, same sampling distribution, same model, same conditions, all that stuff. And we'll get to that in probably the next video. But this is one of the things we're going to be doing in this hypothesis test. Something else you should know before we get started about this test is that, well, in a trial by jury, we assume the defendant, the person accused of the crime, we assume that they are innocent. And we only find that person or people guilty if there's enough evidence to say that they did it, that they are guilty. So we assume they're innocent unless they're proven guilty. In a hypothesis test, we are interested in whether the parameter is greater than, less than, or not equal to a certain value. But we will assume, as we go through the test, that the parameter is equal to the value that we already thought was true. So in this example, we will assume that p is 0.9. Only if there's enough evidence to convince us otherwise will we end up concluding that the parameter is greater than, less than, or not equal to that value. So again, in comparing the hypothesis test that we will conduct to a trial by jury, which you may have not necessarily first-hand experience with, but maybe through media, you've seen procedural dramas, stuff like that. We assume the defendant is innocent, and only are they proven guilty if there is evidence. Similarly, in the hypothesis test, we will assume that the parameter of interest here, p, is equal to a certain value. In this example, p equals 0.9 is what we will assume as we go through the test. Only if there's evidence that our sample is really strange, given that's true, will we prove that the parameter truly is either greater than, less than, or not equal to that value. So, not to get too far ahead of ourselves here, but we are going to assume that the proportion of adult Hoosiers that can identify the current president is 90%, because that's the assumption that we thought was true before we took the sample. We are going to assume that p equals 0.9 when we figure out what model to use for the sampling distribution of p hat. And based on that, only if this sample result is really strange, given that this is true, will we say that we have enough evidence to overturn that original assumption and conclude that p actually is higher than 90%. For more of a big picture view, I said in the last video, and probably ones before that, we're going to be calculating confidence intervals under different situations for the rest of the course. Between confidence intervals and hypothesis tests, such as the one we're about to do, that pretty much takes up everything that we're going to be doing for the rest of the semester. Confidence intervals and hypothesis tests. These two methods of estimating parameters from samples are collectively considered statistical inference procedures. We are trying to infer something about a population, so here the population proportion, based on sample data. Right? So statistical inference is calculating confidence intervals, interpreting them, and all that, and also conducting hypothesis tests and making conclusions from them. Confidence intervals, hypothesis tests, they will go hand in hand. We will compare how those two things are related once we go through how the hypothesis test works for this situation where we have one sample for a population, one sample for a proportion. So, for any hypothesis test, we are going to set up two hypotheses. They are going to be complementary in nature, such that the two hypotheses, either one is true or the other is true. Okay, together they encompass every possibility. The first hypothesis is called the Null Hypothesis. It is denoted HO, or H naught, not being like N-A-U-G-H-T, the word meaning nothing, essentially. The null hypothesis, you can call this H0, 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 whatever you want. Some students, for a reason I can't comprehend, want to call it HO. Whatever. Whatever helps. Call it whatever you want. But this is the null hypothesis. And in the case where we're talking about one sample proportion, the null hypothesis will look like this. It will be that P is equal to a particular value. This is P0, 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 whatever you want to call it. The null hypothesis is that the population parameter, which is the thing we don't know that we're interested in, is equal to a particular value. So in general, the null hypothesis looks like this. For our example here, we will say in the null hypothesis, this is what we are assuming to be true. So H0 for this example is that the population parameter, P, the true proportion of adult Hoosiers who can identify the president, we are going to assume that that is 90%, because that's what it says in the problem. Okay? So for our example, the null hypothesis is that the population parameter is equal to 90%, or 0.9. The null hypothesis is always what we will assume to be true as we work through the test. Okay, so until we have evidence that this is not true, we are assuming that we know what P is. And that's an important point to make, because we don't know what P is. We don't know what proportion of adult Hoosiers know who the president is. That's the whole reason we're doing all this. We still don't know P. But when we do a hypothesis test and we write the null hypothesis, we are now assuming for the duration of the test that P is 0.9. We're not assuming P is P hat anymore. We're assuming that P is 0.9. That's what makes hypothesis testing different from calculating confidence intervals. Remember, for a confidence interval, we assumed P was P hat. That was our best estimate. Now we're assuming P is this. Just to review some of the information we just covered so you can get it in your notes. The null hypothesis is what we assume to be true as we go through the test, unless our sample data ends up proving it false. So again, the null hypothesis is kind of like the boring one. The null hypothesis is just, hey, this is what we're assuming the parameter is, just so we have something to go by. Notice that the null hypothesis, and this will be true for the other one as well, it's making a statement about the population parameter, which in this case is P, right? There could be multiple choice questions on quizzes, tests, or the AP test that are like, here's a situation, write the hypotheses for the hypothesis test. And some of the options will have P hat here. This will never be P hat. For a hypothesis test, the hypotheses are always about parameters. P for proportions, or when we get to talking about means, it will be mu in there, never X bar, right? Because what we're interested in is whether the population parameter is equal to a specific value or not, right? And when you're performing, this test in particular is a one sample z-test for a population proportion, right? If we have one sample and we're looking at a proportion, it's a one sample z-test for a population proportion. The null hypothesis for a test such as this will always have the form HO or H0, P equals P0. P equals a value. It will always have that form. The other hypothesis can change in terms of what it could be, and we'll talk about that in just a minute. The null hypothesis will always be the parameter equals value. That value can change, but it's always P equals something. So we are now familiar with the null hypothesis, but we said the hypothesis test has two hypotheses. The second one is called the alternative hypothesis. So we've got the null hypothesis and the alternative hypothesis. The null is always that P is equal to a value. The alternative hypothesis has different forms that it can take depending on the question that's being asked. So, in general, the alternative hypothesis, which is denoted HA, is that the parameter, in this case P, is either greater than, less than, or not equal to a value. And this value, P0, P0, is always going to be the same value that it was in the null hypothesis. So, the inequality symbol that will be used in a particular example is based on what you want to know. What is it you're interested in proving? In our example here, we are wondering if the sample provides strong enough evidence to suggest that the true proportion is higher than 0.9, higher than 90%. So our alternative hypothesis should be the thing that we're trying to prove. Is the true proportion higher than 90%? So in this case, it would be HA, P higher than is greater than 0.9. If the question had asked if the true proportion is less than 90%, the alternative hypothesis would be P is less than 0.9. If the question we're asking does it provide strong evidence to suggest that the true proportion is different than 90%, not in one direction or the other, but just different than 90%, we would put a not equal to sign here. Okay. So the null hypothesis is always P equals value. The alternative is based on what you want to prove. P could be greater than, less than, or not equal to a value. The alternative hypothesis is always trying to show what we are trying to prove. What is it we want to know about the parameter? Is the true proportion of users that can identify the president greater than 90%? You need to write that as an inequality. That is your alternative hypothesis. P greater than 0.9. Right? So does our sample prove that it's higher than 90%? So we've got our two hypotheses, the null and the alternative. The null is what we're assuming to be true. The alternative is what we're trying to prove. It is possible in some contexts for the hypotheses to be given to you for a hypothesis test. That I've seen that. It can happen. Just gonna drop my marker there. But if you have to perform a hypothesis test and construct the hypotheses on your own, you need to know how to construct them. It's the alternative hypothesis that can change depending on the question being asked. So, there are just three forms for the one sample z-test for a population proportion. You can have P greater than a value, P less than a value, or P not equal to a value. And it all depends on what you want to prove. Are you trying to prove whether a parameter is greater than a particular value? If so, the alternative hypothesis will have that greater than sign. If you're trying to prove whether a parameter is less than a value, your alternative hypothesis should have a less than. And if you're just trying to prove whether the parameter is different than a value, that's when you use the not equal to sign. And again, we will get into some more examples here. For this one, since we want to know if it's higher than 90%, we're using that greater than sign. But I just want you to keep in the back of your mind, there are three different options here for what the alternative hypothesis looks like. There's a little bit of notation regarding hypothesis tests that I want you to be aware of. For the alternative hypothesis having a less than or greater than sign, remember there are only three options, greater than, less than, or not equal to. If it's less than or greater than, we consider the hypothesis test to be one-sided, and the reason for that will be more clear once we actually go through the test in the next video. But for now, you can consider that one-sided because the inequality symbol, either a less than or greater than sign, has us looking in only one direction. We will only show that the proportion is less than the value or greater than the value. We're only interested in one side of things. Alternatively, for an alternative hypothesis that has a not equal to, we are interested in whether the proportion is different in either direction, so we consider that test to be two-sided. So we've got one-sided tests or two-sided tests, and that is dependent upon what inequality symbol you're using in that alternative hypothesis. There's just one more thing that I want to get to in this video, and it's what is the point of this? Hypothesis tests are quite different from anything else we've done in this class or anything you've probably seen in math. Although, if you're familiar with the scientific method, you may actually know where this is coming from, because that's essentially what we're doing. The first step, I think, of the scientific method, I'm getting out of my depth here, I'm a statistician, not a scientist, is to come up with hypotheses. That's what we're doing here. What we're going to do is, we are going to use the sampling distribution model of p hat, like we've done in the past for confidence intervals and for calculating probabilities. We're going to use this sample proportion, 376 out of 400. If we find that that is not very unusual of a result, assuming that p is 0.9, then we're going to say p equals 0.9 seems reasonable. And we're going to essentially say this is okay. We'll get into more specifically what you'll say when we do the test. If, on the other hand, this sample result is very extreme or very unusual, very unlikely, assuming that the true proportion is 90%, then we're going to say this doesn't seem reasonable. And we're going to reject the null hypothesis in favor of the alternative. So we're either going to reject the null hypothesis or we're not going to reject the null hypothesis based on the sample that we have here. How we're going to do that, the mechanics of the test, are what the next video is going to be about. And I think you'll find that we are using what we've already built. Essentially, the rest of the hypothesis test, once you write the hypotheses, is pretty simple. And we've done all that stuff before. We're just giving it a new context here. We're going to use that sampling distribution model to answer this question. And that's what the next video is about. So I hope you're excited. This is some of my favorite stuff in this entire course, and I hope that's showing. I really like confidence intervals and hypothesis tests, and I hope that as you get more comfortable with them, that you will too. So in the next video, we'll actually do the test, and we'll see you then. Take care.